Hi there, I'm Daniela, and this is a summary of the work entitled Deep Generative Analysis for Test-Based fMRI Experiments. First off, fMRI data is typically modeled by fitting a generalized linear model, or GLM, to each and every voxel, or subunit of a brain volume, independently, as shown in this equation. That is, we model our data X as being the product between a design matrix, gamma, which has each column being composed as the convolution between the time series for a given regressor and the hemodynamic response function, or HRF, and a parameter matrix, beta, plus some error, typically assumed to be Gaussian. Once we estimate beta, we take its rows to represent spatial brain maps, capturing the inferred effects of a given covariate on brain-wide activity. We then perform provoxal statistics and false positive correction on these maps to obtain final activation maps, as shown here. We then, in this work, propose a different approach to modeling these data. Essentially, we take entire volumes at a time, as opposed to single voxels, and feed these through a encoder network, which parameterizes the mean and standard deviation of a latent distribution. We then sample from this distribution and feed it through a decoder, which produces a mean volume reconstruction. This mean volume reconstruction can be further broken down, as shown in this equation, namely into a base map, which captures mostly anatomical details, and a set of covariate effects, which can be further subdivided into a gain, modeled by a covariate-specific Gaussian process, and a spatial brain map, also covariate-specific. Additionally, we model variance on a per voxel basis using a separate variance map. First, we tried testing our model's ability to capture a non-synthetic signal. To do that, we took a standard number 3 from the MNIST data set and resized it, normalized, and binarized it. We then used it to create a time series simulating a block design of 20-second blocks and added to a pre-existing fMRI data set. We ran this data for a model using 3 different initialization seeds and 4 different intensities, as you can see here. Our model can capture the peak of the signal, even for lower intensities, and can fully capture both the shape and location of the signal for high enough SNRs. We then tested our model's ability to capture the effects of visual stimulus presentation. And for that, we picked data from the NKI Rockland fMRI database, which is an open database, and chose the checkerboard presentation visual task, which consists of 20 seconds alternating blocks between either no visual stimulus presentation or a checkerboard presentation. We ran this data through both our model, top row shown here, or standard GLM fMRI analysis software, bottom row. As you can see, our model produces a V1 cluster, which is expected for this task, and does so in a smoother manner and producing less spurious activation voxels outside of this cluster. If you found this work interesting, please check our paper. Thank you.